Alrighty, good morning everybody. Welcome back to Math 105. Plan for today is we are going to start Standard 11 and start talking about Euclid's Elements. Kind of work our way through the first few postulates within it. Talking about what do the postulates mean, how can we interpret them with a modern spin, and also start looking at some of Euclid's definitions of things like points and lines, and then talking about how can we actually use these definitions in a way that's going to be useful to us. I've got my next office hours on Monday from 10 to 10:50 and from 2 to 3. As a reminder, exam 2 is going to take place on Monday-ish, which means I will be posting the exam and sending out an email about the exam sometime Sunday evening, probably most likely, or Sunday afternoon. And I expect I'll make it due then Tuesday evening, with the idea that you can use class time on Monday as your hour to take the exam if you want, because we will not be having class on Monday. Also, don't forget the standard 10 quiz is due tonight. As a quiz. It's on my hour. So make sure you've remembered to do the standard 10 quiz. Any questions or comments before we get started today? Okay, so one day a cannibal decides to go out and buy some brains for dinner. Cannibal goes to the butcher shop, where the butcher tells him that a mathematician brain costs $1 a pound, engineer brain costs $2 a pound, and politician brain costs $4 a pound. Cannibal's pretty surprised by this and says to the butcher, "Well, why does a politician brain cost 4 times as much money as a mathematician brain? Is the quality that much better?" Butcher replies, no, it's nothing to do with quality. It's just that it takes a lot more politicians to make that pound than mathematicians. Okay, so in the last couple of classes, we kind of talked about the history of geometry leading up to the time of Euclid, and we discussed a little bit about what Euclid was trying to do in the Elements. Just as a reminder, there's a new packet for today. It looks like everybody's got a copy. But just as a reminder, to kind of set the tone, Euclid's Elements had 4 pieces to it. It had definitions, meaning Euclid tried to come up with definitions for every single term that he used, like lines, points, circles, etc. Euclid had the 5 postulates, which are the 5 statements he assumed to be true, and then built all of his other math off of these original 5 statements. He had his 5 common notions, which were, again, 5 statements that Euclid never proved that were sort of laws of logic that Euclid ended up relying upon in several of his proofs. And finally, he had roughly 400 propositions spread out across the 13 different books within Euclid's Elements, where I think it's like 450 something. It's in the 400s, I know. Where these were the mathematical statements that Euclid was able to prove, but using only his postulates and his common notions. So he ended up needing to really just assume these 5 basic postulates, as well as some laws of logic to start, and assuming those statements were true, he was able to actually prove hundreds and hundreds of these propositions. So, well, I thought where we could start off is trying to look at some of Euclid's definitions. Because Euclid tried to define all of his terms carefully, but no one had ever really tried before Euclid to come up with a precise definition for what is a point, what is a line, what is a circle. People are like, this thing's a circle. They tried to define circles before Euclid using like examples of like, the circle is a thing that looks like this, or a line is a thing that looks like that. Nobody nobody ever really tried to come up with a careful definition. It was sort of like before someone was able to come up with the definitions for even and odd that we used, people were like, oh, even means it's like 2, 4, 6, 8, 10, etc. Or odd is 4, 1, 3, 5, 7, 9, 11, etc. Kind of used, before Euclid, all these different terms were kind of defined using examples of like, here's what odd numbers look like, here's what even numbers look like, without anyone actually going through and trying to come up with a careful definition like, oh, a number is even if it is equal to 2n for some counting number n. And the same was true with lines and circles and such. So Euclid had to try and come up with some of these initial definitions on his own. And you could tell he struggled with it. So let's try and look at some of Euclid's definitions. A point is that which has no part. A line is breadthless length. Anytime you see me underline on the board a word in one of these definitions, that's just going to be a word that that's the thing we're defining. So here I've underlined point and line because we're giving definitions for those two words. As we're going to see a trend, I think, going through a lot of Euclid's definitions, and the trend is going to be, if you try and read the definition for the first time, it'll look at it and go, huh? At least that's certainly true for me. Like, a point is that which has no part. What does that mean? What does it mean to say a point is that which has no part to it?
You're saying part as in like it doesn't split up rather than pieces?
Exactly.
No part.
You can't split it up into multiple pieces, into multiple parts. It's that which, in other words, I would say that what Euclid is trying to say when he says that a point is that which has no part, he's saying it's the smallest possible geometric shape. That can't be split up into smaller pieces. So in other words, you could always take a line segment like this one, and you could say, I can cut this into smaller pieces. I can cut this, say, down the middle, and make two smaller line segments out of this line. Out of this. I could take this circle and cut it in half down the middle, split it up into two halves, two semicircles. But with something like a point, there's nothing really that you can split in half. I can't cut a point in half down the middle. It's infinitely tiny, and so it makes no sense to say, how can we divide this point up into smaller pieces? There is nothing smaller than a point. It'd be, before the invention of subatomic physics, for instance, it'd be like trying to say, I have an atom, the smallest possible thing in the universe, and I'm going to cut the atom into pieces. Well, for a long time, can't do that. There's nothing smaller than an atom. Same sort of thing with looking at a point. And so that's how Euclid tried to define this sort of point, is just that which has no part, that which can't be divided into smaller pieces. Next one is that a line is breadthless length. Another one that's a little bit tricky, I think, to try and take apart and piece apart. What is Euclid trying to say when he says that a line is just breadthless length? Here we go.
Is he trying to say that both ends go up infinitely in either direction?
Both ends go off in either direction. Actually, I don't think so. For the main reason that through Euclid never looked at infinite lines. Whenever Euclid talked about something that's a line, we would now define, or we would now in kind of modern times call a line segment, like a line which is like something that has a finite start and an end to it. So to Euclid, this would be a line. And something that goes off forever in both directions would be something Euclid didn't think of. It wasn't until much more recently that we started referring to the things that go off forever in both directions as lines.
I think doesn't breathless that I'm not even trying. Length mean that
It's a mouthful.
that it's not deviating perpendicularly from the line at all. So it's continuing in the same direction and it has no width to it. It's always just that line. Like it doesn't curve at all.
I would say, yeah. I'm going to agree with part of what you said. And said when it says breadthless, it basically means something with no width to it. It's basically just a one-dimensional object. It's something that's infinitely skinny. Here's my students. So basically, I think Euclid is trying to define a line as being something that's one-dimensional, something with no width. No width or height, just length. And so, as an example of things Euclid would call a line, something like that. Something that starts and ends and has zero width to it as we work our way along the line. So here's a plot twist. Here's something else Euclid would consider to be a line. Because to Euclid, when saying that a line is breadthless length, meaning if a line is taken to be some sort of one-dimensional object that has no width to it, only length, that doesn't necessarily mean it can't deviate its direction at all from this definition. A line could just be something that kind of curves and wraps around somewhat. Here's another example of a line. Straight up circle to Euclid would be considered to be an example of a line because it is something that has no width to it. It starts and ends at the same point, but is infinitely, the shape itself, I would say, is infinitely skinny. And so, Euclid is very much defining lines in a different way than how we would define lines in modern times. If we want something that doesn't deviate in direction, then we need what Euclid would call a straight line. This is going to be our third one. A straight line is a line which lies evenly with the points on itself. And so a straight line would be the sort of line that would satisfy just this first requirement, or that this first thing would look like, something that doesn't change direction, but wouldn't satisfy the second and third. So in other words, I would say a straight line is a line that never changes direction. In other words, it's a line that looks something like this, but not something like that that has curves. To Euclid, the second thing would be called a line, but it wouldn't be a straight line. Euclid's already screwed up. We in modern times, we don't know anything about Euclid and how he kind of really wrote the elements that much. But in modern times, mathematicians kind of tend to think that Euclid wrote his definitions before coming up with most of his postulates. Because it turned out Euclid never really ended up using this definition at all, that a line is breadth length. He pretty much, anytime Euclid talked about a line in any of the postulates or any of the propositions, he always used the term straight line. So we're never going to be talking about lines that do the sort of weird, wacky curving to them for the most part. There's a couple definitions where it'll show up. But for the most part, Euclid always just stuck to saying straight lines. And so now, modern mathematicians tend to think Euclid came up with this definition for a line before he came up with any of the propositions because he never ended up really using it there along the way. By the way, a common line you're going to hear me say for the rest of the semester is, here's a case where Euclid screwed up. Turns out, trying to be the first person to define this sort of careful, logical system where you prove everything, if you're the first person to do it, it's kind of a hard task. You're probably going to make mistakes. And so at several points throughout the semester, we're going to point out times when Euclid did, in fact, make mistakes. So next up is a circle. This one's a fun one. A circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lying within the figure equal one another. So out of curiosity, when you were first learning, back when you were a kid, what a circle is for the first time, how many of you saw a definition for circle that looked anything like this? Well, how did you see a circle defined?
I think my mom said, I was in school, it was a line within a loop. It kept going, it didn't have an end or a beginning. Per se, it was a line that was curved.
Okay, so sort of like a line that kind of looped back around itself and kind of started and ended at the same point, say?
Well, she actually said it didn't, like, obviously to draw it, there was a certain end point, but like, formally speaking, it didn't have a beginning point.
Okay, gotcha. Just that it didn't have a starting point or end point. It's just something that loops around back on
Once it was
itself.
drawn, you shouldn't be able to tell where her end point was.
And I think that's a good intuitive way to sort of try and see this is what a circle looks like. It's something that looks like this. Euclid wanted to try and come up with a careful definition for what he believed circleness to be. And this is what he came up with. A circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lying within the figure equal one another. So here is what this really means. The one point that's in our that the definition refers to is going to be the center of the circle. And so what this means is if you take a point, and this is going to be our center, it's basically saying anytime a circle is going to be a shape that you get from taking a single line So here, this outer boundary is a line. It does satisfy Euclid's definition of a line because it's one-dimensional, no width. And a circle is that which satisfies if you take any line that starts at this one point, the center, and ends on the outer circle. So a line that goes from here to here, from here to here, from here to here. You're always going to get lines that have the same length, according to Euclid. So in other words, it's a plane figure. Plane figure to Euclid just means something two-dimensional. Contained by one line. The one line is going to be the outer circle, such that all the straight lines falling upon it from one point, meaning all the straight lines that start at this point called the center and that end on the circle itself, all the straight lines falling upon it from one point, all these straight lines, among those lying within the figure, meaning all these straight lines are inside of the circle itself, all the straight lines falling upon it from one point among those lying within the figure equal one another. So he's basically saying all of these straight lines from the center to the outside circle are equal. What do you think Euclid means when he says that all of these straight lines from the center to the outer circle are equal? Equal in what way?
Oh, they're the same length, and so therefore the circle is symmetrical. It can't be kind of like an oval.
Bingo. Yeah, they're equal in that they have the same length to them. Like, Euclid never defined what it meant for two lines to be equal, but it basically ended up, you can kind of figure out from context that what Euclid really meant is that they're the same length. They have the same size to them, so to speak. These are a few of Euclid's definitions. There's actually something like 20, if you look at Elements Book 1, there's actually like 20-something definitions just in Book 1. These are kind of the only ones we need for the first three postulates. I'll give you some more definitions in Standard 12 once we start looking at angles. But I didn't want to overwhelm you with definitions all at once. I kind of wanted you to get a sense for how did Euclid write down his definitions. And typically, the way Euclid wrote down a definition is in a way that doesn't immediately make sense, and you have to really stop and kind of think about what is he actually trying to say. It's because it's hard to come up with intuitive definitions for things like point and line and circle in ways that are kind of make sense and that are in a way that kind of makes sense and is useful. So just because our definitions for things like even and odd might be, oh, it's just 2 times n for some n, or 2n plus 1 for some net counting number n. It's a little bit harder to come up with definitions for these simple sorts of geometric shapes. Euclid had to come up with this mouthful of a sentence here. So, any questions about any of these definitions? Okay, let's move on to the next page. So, you remember back in the previous standard, I said that Plato thought that the ideal geometric shapes are lines and circles? Euclid kind of took that to heart, and that Euclid tried to write the elements in mind with the idea that lines and circles are the most important of geometric shapes. And so Euclid actually took that into approach in that all of his propositions, all of his, and many of the postulates are going to be written in mind with the idea of how can you construct a line and how can you construct a circle. And in doing so, I'll say that Euclid thought of geometry constructively. And And by constructively, Euclid wanted to be able to talk about having ways to construct geometric shapes using his postulates and using his propositions. So using his tools, Euclid wanted to know how to physically construct geometric objects. And there were two kinds of actual physical tools that existed at the time of Euclid that Euclid wanted to be able to base his postulates and base his propositions around, and that's the straight edge and compass. So straight edge is basically just something with a straight edge to it. How did I define it again? It's a device used to draw a line segment between any 2 points or to change the length of line segments. So a straight edge is just going to be some tool. I'm going to use my joke book as my straight edge. Straight edge is just a tool where if I'm given 2 points, let's say point A and point B, straight edge is a tool I can use to help me draw the straight line that passes between them. If I just try and draw it by hand, I'll probably wobble a little bit, and it won't entirely be straight. But if I use my straight edge, page 7, what I can do is I can line up the straight edge on point A and point B, and then kind of just pressing up against it, use it to draw a line that would be much straighter than if I had tried to draw it by hand. And similarly, if I have a straight edge, and if I already have a line, I can use the straight edge to actually make the line longer by just holding up the straight edge against the line and using it to extend the line in that way. Pro tip, Dr. Gersel I am not a pro straight edge user. So you will see me try and use a straight edge and make little mistakes like, it's not exactly on top of the same line, but straight edge is a tool that can be used to draw straight lines in general. And that was a tool that existed at the time of Euclid. The other tool that existed at the time of Euclid is this thing. Like a weird whacking stick.
Chopsticks.
It is like chopsticks, except I am not going to eat with this because contrary to popular belief, mathematicians do not actually eat chalk. So this is a compass. And compass is basically a device that can be used to make circles. And the way a compass works is you have to be able to pick what point you want to be your starting point, or the center of your circle. So let's say I want that to be the center of my circle. And then you have to set a radius for a circle. Let's say I want this distance right here to be the radius of my circle, how far it is from the center to the outside points on the circle. And then the compass, let's tighten this up, is just going to be a tool that you can use to make a circle of that radius. And I'm not used to doing this. This could go horribly wrong. Like so. That was hard. Cool. Thank you. do not expect me to actually use this throughout the rest of the semester. In theory, I would be using this for the rest of the semester to construct perfect circles on the board, but as you can see, this is not the best thing for drawing circles on the board. But a compass is not like, it's not like a compass that tells you which way is north. This isn't a Zelda game, unfortunately. I love Zelda. A compass here is just going to be a tool that's used to draw circles. That can draw any circle you want as long as you know where the center of the circle is and what you want the radius of the circle to be. Because if you know what the center is, I picked a point that was right here, and I picked the radius of the circle to just be this distance right here. With that in mind, you can then use the compass as a tool to draw theoretically perfect circles. Circles where all the points on the circle are the same distance away from the starting point. So Euclid actually wrote the elements with straight edge and compass in mind. Those were tools used by geometers from the academy in his day. And so one comment I will make is that Euclid intended that his propositions and postulates were based around the idea of how you can use a straight edge and compass. Because Euclid assumed that if you're someone who is trying to do geometry, these are tools that you are going to have on hand and be able to use. And so, with this in mind, Euclid is basically just saying, and with this in mind, a lot of the elements, especially the first book, which is on two-dimensional geometry, is based around the idea that you're using straight edge and compass to construct the sort of shapes that he wants you to construct in order to be able to write these sorts of proofs. Anybody have any questions or comments about straight edge or compass? So in theory, anytime I drew a shape for the rest of the semester on the board, I would have a straight edge and compass on hand to make them look nice and pretty. That takes a lot of time, so we're just going to be assuming I'm using a straight edge and compass and I'm just going to try and draw things by hand that are not going to be as smooth as it would be with straight edge and compass, if you can call this circle I just drew smooth. Okay, so now we're ready to start looking at the 5 postulates. Page so long. Let's look at postulate 1. I split up the 5 postulates, by the way, into 2 separate standards. This standard 11 is about postulates 1 through 3. Standard 12 is going to be about postulates 4 and 5. Because postulates 4 and 5 are more complicated and very different from the first 3, especially postulate 5. That one's the scary one. First 3 postulates, I think, are fairly straightforward and are all kind of based around this idea of straight edge and compass. Postulates 4 and 5 have more to do with angles, and that'll be in a packet that we look at next week. All right, postulates 1 through 3. So for each of these postulates, I'm going to write down the version of it that was that Euclid came up with, and then I'm also going to write down a more modern version of the postulate, written using kind of more modern, maybe a little bit easier to understand language. because some of Euclid's postulates are a bit, not these first three, but the later ones are getting very technical. So here's Euclid's first postulate. To draw a straight line from any point to any point. So, I know I told you up front that all the postulates are mathematical statements that Euclid assumed are true with no reason to back it, with no kind of logic to back it up. Is that a mathematical statement?
It's not a complete sentence.
It's not a complete sentence. To draw a straight line from any point to any point, that's not really making any sort of claim. It's just saying drawing a straight line from a point to a point. What does that mean? Does it mean you can do it? Does that mean you have to do it? Does that mean any straight line has to go from a point to a point? You could kind of, technically for all of these postulates, Euclid had like the words out in front. It is postulated that. Or it is postulated. So it is postulated to draw a straight line from any point to any point. But what Euclid really meant by that is it is possible. It is possible. It's possible to draw a straight line from any point to any point. And that's the first statement that Euclid just assumed is true in developing his logical system. Meaning, in other words, that if I have a point here P, and if I have a point here Q, Euclid said, I'm going to just assume, with no justification for it, that I can draw a straight line that starts at point P and ends at point Q. Or Dr. Hurstel is going to cheat and try and draw a straight line and move point Q so that it actually ends up on the straight line. But according to Euclid, Euclid believes, says without any sort of logic to back it up, it's possible to do this. You give me 2 points, I can draw a straight line that goes between them. And please don't give me 2 points that are very far apart, as that will take a lot of pencil, or in my case, chalk, to do that. I think that the first postulate is sort of taking Euclid's constructivist attitude in mind, and that it's saying it's possible to construct something. It's given 2 points, it is possible to construct the line that goes between them. Euclid made a mistake, by the way, in writing his postulate. And the mistake is not that to draw a straight line from any point to any point is not a sentence. That's okay. But I'm going to write down a more modern interpretation of Euclid's first postulate. And I want you to try to tell me, what does the modern version have that that Euclid's version does not? So here's what the modern version has. It says, the modern version says, for every point P and every point Q not equal to P, there exists a unique line that passes through P and Q. It's a very similar sort of statement, but there's a subtle difference to it. So what I'd like for you all to do is I want you to think for just a minute or so and see if you can find one key way in which the modern version of Euclid's first postulate differs from Euclid's version. Yes, I see you have your hands up. Go ahead. I just want to give everybody a chance to think about this for just a minute, and then we'll come back and talk about this as a class. But in particular, there's one key word in the modern version that makes the modern version different from Euclid's version. Well, how is the modern version different from Euclid's version? Anyone want to give it a go? Say, Pat, I saw your hand up earlier.
There's two things, I think. One, it says is every point Q not equal to P. So with Euclid's definition, it's possible to just superimpose 2 points and then say, okay, draw me a line. And that's, yeah.
So this is our P, and this is our Q.
Yeah.
Then Euclid is saying, yeah, I could draw a line from this point to this point. Here's the line. Okay? That's certainly something that I would say doesn't look like a line. So maybe Euclid's postulates would say something like it goes from any point to any other point. To make it clear that like when we're drawing straight lines, we're not starting and ending at the same place. Technically might describe a straight line, but not the way that we're used to thinking about it. You mentioned 2 things. What was the other thing you mentioned?
The modern definition, or Euclid's definition says from any point to any point. The modern definition says through the points.
Yeah, it says it passes through the 2 points. So that's just mainly due to the fact that nowadays what Euclid described as a line, we would refer to as a line segment. And so in the modern version, with lines going infinitely far in 2 directions, we might just say, yeah, we really mean, in modern times, we're saying there's a line that goes on forever in both directions that happens to pass through the points P and Q. You're right. That's just mainly due to how we define line differently nowadays, as opposed to how Euclid defined line back in his day. It's not really, I would say, something that's a significant difference between the 2 postulates in terms of meaning, more just it's something that refers to different meanings from how we define line versus how did Euclid define line. Good observation. What else is different from Euclid's original postulate to the modern version?
I noticed in the modern version, the word unique describing the line, essentially telling us there is only one line that can be drawn between 2 points.
Bingo. And here, I think, is the main way that Euclid made a mistake in writing down his first proposition. Euclid neglected to say the word unique. Because if I have 2 points, P and Q, assuming I have to draw a straight line, a line that doesn't change direction and starts curving on me, there should only be really one way to draw a straight line between these 2 points. And that's that line. Anything else is either not going to start or end at the same places, or it's going to have to curve and not be a straight line because it wibble wobbles around the way. I say that Euclid made a mistake in not mentioning the word unique because Euclid heavily relied on the fact that there is only a single line throughout many of his propositions. Euclid assumed that there's only one line, but he never mentioned that in the first postulate. Euclid himself never used the word unique, but he did heavily rely upon that later on. And so that's why I call that a mistake, is because Euclid assumed something that he didn't actually write down. He's kind of missing something in his first postulate that he needed later on in proving propositions.
What are some errors we could see down the road with there being an opening for the possibility of 2 lines with this definition?
The main error comes from the fact that later down the line, we're going to have a lot of times two lines that we want to show are the same, have to be the same line. And it's going to come down, and oftentimes proving two lines are the same comes down to the fact that they start and end at the same points. And Euclid often says, oh, these are two straight lines that started and ended at the same points, therefore they have to be the same. Which would be something that logically has to be true. Yeah, if you have two straight lines that start and end at the same points, they logically have to be the same by the modern version of Euclid's first postulate, but not by Euclid's version. So that's going to be kind of something we see several times once we get a few standards from now, is that Euclid kind of relied on his lines being unique, but he never explicitly said so. So Euclid assumed uniqueness but never explicitly said so. I'm going to try and make it a key point throughout kind of the rest of the semester to point out times when Euclid made mistakes like this. Not because I want you all to come out of this class thinking Euclid was an idiot. I want you to realize that when Euclid did this for the first time, it's a hard endeavor to come up with a logical system of geometry that works. And so if you're doing this for the first time, no one else has ever really done this, you're going to make mistakes along the way. You're not going to do everything perfectly, and Euclid is still considered to be a great mathematician, but even he made plenty of mistakes along the way. So don't feel bad that you all make mistakes. Even Euclid screwed up. Euclid's a lot more famous than any of us, I think, so far. Any questions about the first postulate? Okay. Have a good weekend. I'll let you go a few minutes early. Okay, like three minutes is not really enough to do the second postulate justice. So when we come back on Wednesday, we'll talk about the second and third postulates. Those are both pretty quick ones. And talk a little bit more about some of the consequences of the first three postulates. And then on next Friday, we'll be ready to move on to talking about the fourth and fifth postulates. All right, have a good day, everybody. Or have a good weekend, everybody. I will see you all on Wednesday. And I'll be sending out an email with instructions about the exam later this weekend. Probably you can expect that on Sunday sometime.